Hey guys, this is Mr. Bennett and this is Unit 13, Video 2. We're going to talk about chemical reactions and enthalpy. So the first idea that I want to put out there is that all chemical reactions involve a change in energy. So in other words, all chemical reactions involve either an absorption or release of energy. Now I've got two graphs here to kind of depict that. The graph on the left is showing what we call an endothermic reaction. And the way I remember what an endothermic reaction is all about is that the En in endo, think of it as being short for enter. So in this case, energy is entering the reaction, or we could think of it as it's absorbing. Okay, endothermic reactions absorb thermal energy. So when we look at the graph here, the reaction pathway is going from left to right. So in other words, this is the start, or if we want to think of it in time, this is time 1, the initial time, and then this is the finish. Okay, so we wind up with our product here, and so that would be like time 2. Anyhow, so as time goes on throughout a reaction from beginning to end, the potential energy is going to change. Potential energy, think of it as the stored energy, the energy that's found within the chemicals that are either reactants or products in the reaction. So our reactants are starting off with a potential energy here, and our products, their potential energy is right here. Right? So you can see that there's a net or an overall gain in energy from the beginning to the end, from the reactants to the products. Okay? And this diagonal here, that actually kind of coincides with the reaction. So in other words, we have our reactants, they go through the reaction, right? And then we get our products, which have absorbed energy. Okay? Now the opposite of that would be an exothermic reaction, and I think of the EX in exothermic as standing for exiting. So in an exothermic reaction, they actually release thermal energy. And you can see that in this graph where we have the reactants, which have a potential energy up here, and the products have a lower potential energy. So we've actually lost or released energy over the course of the reaction. Okay, so that's endothermic, exothermic. Now, this is taking into account the fact that this whole reaction had kind of a total heat. Okay, so there's a total energy, if we were to put all this together, the energy of the original reactants, the energy of the products, and the energy that was either released in the case of an exo, and the energy that was gained or absorbed in the case of an endothermic reaction. So if we're to put all that together, the heat of the products, the heat of the reactants, the energy change, we call that the total heat of the system, and that is called enthalpy. Now the symbol for enthalpy, because it's the total heat, is a capital H. Okay, so think of it as H for heat, but it's a capital H because it's the total heat. Now it turns out calculating the total enthalpy is actually kind of difficult because you have to figure out the heat of the substance as well as the heat change involved. Okay, so it's kind of difficult to figure that out. But looking at just the change in heat, this guy here, that's not so bad. And so we call that the change in heat of the reaction, also known as the change in enthalpy, or if we want to do it nice and simple, we use a delta sign because deltas mean change, and then a capital H for enthalpy. Okay, so if we apply that to a chemical reaction, let's slide this up here. What that means is that, again, we're looking at the change in enthalpy, which is the change in heat of the reaction. We can look at a reaction like this and we can see that heat here was actually released. We had the original reactants, right? And then the reaction occurs and we get the products. And one of the products, these are products, is heat. Okay, 890 kilojoules. So since heat is leaving as a product, we would say that this is an exothermic reaction because heat is being released. Okay, if heat had been on this side, then it would be an endothermic reaction because heat would be going into the reaction, it would be absorbed and become part of the products. Okay, now in this particular case the heat is written as part of the reaction, but we don't always do that. Sometimes we write out the reaction itself, so in this case aluminum oxide reacting or decomposing into aluminum and oxygen gas, and then we make a note that the change in enthalpy or the change in heat is a number. Okay, so if this is the case, what you actually have to do is you have to kind of put this into the equation to figure out what's going on. So in this case, notice the change in enthalpy is a positive value. Okay, and so what that means is that the heat of this system, the heat of this reaction, is going up, which means that the heat has to be absorbed, right? So if we were to add this delta H, or this change in enthalpy, into the reaction, we would put it on the left side because heat is being absorbed. It's a positive value. And notice I put a little plus sign here, so I would say 3,352 kilojoules plus blah 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 produces aluminum and oxygen gas. Okay, now let's say that this was different. Let's say that this was negative 3,352 kilojoules. Well, that would mean that we're losing heat, or it's being released, in which case I would put if I were to add this to the equation, I would put it on the right side of the arrow. I would make it a product because, again, it's being released. We're losing the heat. But notice, the change in enthalpy was negative, but when I plug it into the equation, I always use a plus sign, because in the chemical reactions, we always use plus signs between reactants and plus signs between products. You don't see negative signs in a chemical reaction equation. Okay, so when you look at the delta H, the negative or positive is telling you whether it's exothermic or endothermic. If it's positive, think of like the substances are gaining it, so it's absorbing or it's acting as a reactant. If the sign is negative, that means it's exothermic, which means you're releasing it, or it's going to be a product. Okay, so let's put that into this chart here. So an endothermic reaction, remember En stands for enter, so that means the heat flow is entering. Okay, so it's going in. And then exo, remember Ex stands for exit, so the heat flow is going out. Okay, in terms of an equation, if heat is going in, that means that it's going to act as a reactant, because reactants go into the reaction, right? And in exo, the heat flow is going out, so therefore in the equation, exothermic equations, heat is going to act as a product, because products come out of the reaction. Okay, and then as far as the delta H sign, so in other words, when we write it like this, okay, endothermic reactions are going to have a positive delta H, and exothermic reactions are going to have a negative delta H, because you're losing it, it's exiting. Okay, so the last idea I want to get across before we're done here is that because we can put heat into chemical equations like this, that means that heat changes can be expressed in balanced chemical equations. Okay, so here we have iron oxide reacting with carbon monoxide to produce iron and carbon dioxide, and then we have our delta H. So we can actually plug this in. Now there's a negative, notice this negative sign here, so that means that if we were to plug this into the balanced equation, right, negative means we're losing heat. Okay, so it's exiting, which means it's exothermic, and it means that our heat is going to be a product. So if I just add it in here, remember, between products and reactants, we always have plus signs. So I'm going to do plus 26 kilojoules. Now I have a nice balanced equation. Notice the coefficients are already here for us, and the energy is here. Okay, it turns out this energy number here works just like the coefficients. So when you want to convert from something to another, normally we would convert from, say, like iron to carbon dioxide. You can actually go from iron to energy, and you use the value for your heat here, just like you would use the coefficient. So here we have a sample problem that says how much heat is released when 6 moles of carbon monoxide reacts. Okay, if you want to think of this in terms of stoichiometry, going from heat to moles, or moles to heat. Okay, so moles to heat is a one-step equation. Okay, so let's set it up then. Our given is 6 moles of carbon monoxide, so I would write 6 moles CO for carbon monoxide. We know it's a one-step equation, and so they want us to wind up with heat. So heat is right here in the equation. That means our units for heat are going to be kilojoules, because the units in the equation for heat are kilojoules. Okay, and then we need to fill in the bottom here. Well, we need these moles to cancel out, so we're going to put moles, and the substance is carbon monoxide. And then to figure out the numbers here, we go to the balanced equation. So for kilojoules, the number is 26, and for moles of carbon monoxide, the coefficient is 3. So we plug that in. The 6 and the 3 are going to reduce, so 3 is going to go to 1, 6 is going to become a 2, so we're left with 2 times 26, which would be, and moles and carbon monoxide cancel out 2, right? So 2 times 26 is going to give us 52 kilojoules. All right, so that's how we can use stoichiometry combined with thermochemistry to predict how much heat is going to be absorbed or released by a reaction. Now notice there's one more sample problem down here. I would like you to answer questions A and B on your own for practice, and then when you do your whisk, you're going to enter these two answers in at the very end of the whisk. Once you submit, the submission page at the end that says your whisk has been submitted will give you the answers so you can see if you were right. Okay, so make sure you complete your whisk, and we'll see you.